I don't remember if we did the binary memoryless source or not. Maybe we did, but I will start recording from here. So we took one example where we tried to calculate the entropy in this example. So we said you have a source which is producing zeros and ones at any point in time, and there is no relation between the probability of producing a 1 or a 0 at this point, depending on what was the previous value. So that's why we call it memoryless source. The probability of a 0 or a 1 at any point is totally independent from the output at the previous point, okay? So it does not have any memory, no relation between current probabilities and previous outcomes, okay? If we call the probability of producing a 1 from that source small p, as we see it here, then the probability of producing a 0, which we can call it q, but eventually we know that that q is simply 1 minus p, okay? Because the two probabilities have to add up to 1. It's either producing a 0 or a 1. There is no other possibility, okay? In that case, the entropy per the definition is going to be the probability of the first outcome, right? Log to the base 2, 1 over that probability, plus the probability of the second outcome, which is the 0, and that probability is 1 minus p, as we see here, multiplied by log 1 over that probability as well. This equation, if you plot it versus p, the value of p, it's a function of p only, that's the entropy of this source, you will see that it reaches a maximum around p equals 0.5. So the ultimate case, the case that has the highest entropy, which means that case that has the highest uncertainty, is the case when the 1 and the 0 have equal probability. So at any point in time, you have no clue which one is going to come. If you have one of them with higher probability, you expect, as you repeat the outcomes from this source, to get more ones as opposed to getting more zeros. Or the other way around. If the probability of 0 is higher than the probability of 1, you expect at any point in time that it's more likely now that I will get 0 than getting a 1, because there is a higher probability of getting a 0, and so on. Okay, so in both sides, if p is greater than half or less than half, you have lower than the maximum value here. And you can prove this maximum value without graphing it by going through this equation, taking the derivative with respect to p and equating that with a 0, and then solving for p, and you will get for that solution p is equal to 0.5, okay? So that's how you get the optimal or the peak or the minimum of an equation, as you know it already, called optimization, okay? There's another example, I think also we have been through this example, which asks you to calculate the entropy of this source, which is producing one of 5 possible outcomes, the letters A up to the letter E, okay? And then instead of giving you the probability of each one, it gives you the frequency of repetitions of each one. So you have 4 times an A is coming out, 5 times a B is coming out, 2 times for C, 1 time for D, 1 time for E. Now you just need to convert these frequencies into probabilities in order to be able to calculate the entropy. How do you do that? The probability of an A is going to be 4 divided by the total number of outcomes, which is 13 in this case. Probability of a B is 5 divided by the total number, which is also 13, so 5 over 13, and so on. Now you have the probabilities, then you just plug them into the formula for the entropy. P times log to the base 2, 1 over P, or minus P log P directly, okay? Here we use the minus sign instead of flipping the probabilities. And that, adding those together, you should be able to get the H for this source. By the way, H is not going to be negative, even though you have a negative side here, but all these logs are logs of numbers that are less than 1, so they will give you negative. Each one of those is going to give you a negative, so the end result here is going to be some positive number. And in fact, there are 3 properties of H, right? H is always greater than or equal to 0, it cannot be negative, and H is less than or equal to log to the base 2n, where n is the number of possible outcomes from the source. So in the previous example, n is equal to 5. So H is going to be less than or equal log to the base 2, 5. Okay? In that previous example that we looked at. And it's always greater than or equal to 0. When will H be equal to 0? When a source will have an entropy equal to 0.
Well, there is only like the probability of one of the components 100%.
Yeah, so the source is deterministic. It's always doing the same thing. It never changes. So for example, previous source, if it's only producing the letter A all the time, then that source has a 0 entropy. And in fact, in that case, there is nothing to communicate from that source. Just knowing that it is there, you don't need to read what it is producing because you know all the time it's producing A. So I don't need to get any communication, right? Okay. You only need communication if you don't know what's happening there at any moment in time, okay? And it's going to be the upper limit when what happens? Yeah, when all the outcomes from the source have the same probability, so they are equally probable. The difference between those two values, the maximum value possible for the entropy and the actual entropy, for example, what we calculated in the previous, the one that includes the 5/13 and the 4/13 and so on, the difference between that number that we get and the maximum possible number is called the redundancy of that source, and this is the amount of required bits that you can remove by using lossless compression, for example, by using Huffman coding, okay? So when you do Huffman coding, your objective is to reduce H by a value equal to this. Sorry, to reduce whatever coding you are doing to a value equal to H. Okay, so this is the amount of reduction that you can achieve. Okay. There is another variation of entropy called the relative entropy. Typically, we use relative entropy as a mathematical operation to compare two probability functions. So, for example, let's say that I have for the source, like the random variable u coming from the source, I have a probability distribution which is the previous one that we had, for example, 5/13, 4/13, 2/13, 1/13, and 1/13, right? And we call this P of u. And another distribution, another possible distribution is going to be something like 1/5, 1/5, 1/5, 1/5, 1/5. So all are equally probable, for example, or any other distribution other than this one, right? Now I want to compare those two distributions, P of u, and let's call this Q of u. Okay, I want to compare them. Okay, the comparison here is going to be carried out by doing this, like going through this formula. So the distance between P and Q reference to Q, so Q comes as the second, okay, is going to be equal to, right, the probability P, right, which is this value or this value and so on, summation of the probability P multiplied by log to the base 2, the probability P over the probability Q. So this is going to look like this, okay? It's going to be 5/13 multiplied by log to the base 2, 5/13 divided by 1/5, right? This is P, this is Q. Q is always 1/5 for any possible value of the random variable u, right? Plus the next stage is 4/13 log to the base 2, 4/13 divided by 1/5, and so on. So each one of those probabilities is up here and outside, and the other probability of Q is down here. What if it was D of Q reference to P? Then it's going to be the other way. 1/5 times log to the base 2, 1/5 divided by 5/13. So it becomes Q multiplied by Q divided by P. Okay? So if it was this way, then you flip everything. So rather than being P over Q and you multiply by P, in this case, it will be Q multiplied by log and then Q divided by P of u. Okay, of u.
Doctor, one of them have to be like equal probable or it's
No. Any two distributions.
But we take them in sequence. Yeah.
Yes,
The first one is
for each possible value of u, the probability from this distribution and the probability from this distribution, okay? Now, if this number is greater than 0, then this means there is some dissimilarity between the two random variables. They don't look the same. It's going to be equal to 0 if they are exactly the same. So both of them were either this one or that one, right? Both of them. In that case, it's going to be equal to 0 because the P over the Q is going to always give you 1. 1 inside the log will result in a 0, right? And the higher that number is, the more there is a big difference, a big dissimilarity between the two distributions, okay? So it's a measure of the similarity. When it's smaller, it means there is a very high similarity. When it is bigger, it means there is a large amount of dissimilarity. They don't look the same. They are quite different from each other, okay? That's the meaning of the relative entropy. We are not gonna use this too much in what we do here, but it's an important quantity to be aware of. The more, yes?
Again, if it's smaller, they are similar?
They are similar. And if it comes to 0, it means they are exactly the same. They look exactly the same, the two distributions, okay? That's the only case it will be equal to 0. Otherwise, the greater it is, the more they are different from each other, dissimilar to each other, okay? The more important quantity is the conditional entropy. And the importance of this quantity comes from its actual interpretation in real communication systems, okay? So let's look at the quantity first, which is the conditional entropy, and then let's try to see how this allows us to evaluate a communication system and a secure communication system. The quantity is called the conditional entropy, and it's written as the entropy of either x given y or the other way around, h of y given x. And these are two different quantities. They are not the same, okay? So what does it mean? It means the amount of uncertainty I still have about x when I fully know what's the value of y, okay? Where x and y are two random variables that might be related to each other or might not be related to each other at all, okay? Now, so remember the meaning again. H of x given y means the amount of uncertainty about x given that I know y completely. I have y in my hand now, okay? I can see what's the value of y. Knowing this, how much I know about what's the current value of x, okay? Now, if knowing y allows me to completely know what's x, then this quantity is gonna be equal to 0, because there is no ambiguity about x if I know y, okay? An example of that is gonna be a very simple error-free system, okay? Let's say, for example, I have a box, and out of that box, you are picking one of 5 possible numbers, and I have a table that shows you number 1 means that you will get the green ball. Number 2 means that you will get the yellow ball. Number 3 means you will get the red ball, and so on, okay? So if you get a number from there, and assuming that this number is y, this is what you are given. So you pick it from the box, and you know now that the number is 3. Do you have any doubt, given that table that you see there, that you will get the red ball? Because I already told you on the table that if you get number 3, then this means you are going to get the red ball, right? So that's a very deterministic case. Knowing y, knowing that number, allowed you immediately to know what's going to be the value of x, right? In that case, h of x given y is going to be equal to 0, because knowing y allows me to deterministically know what's going to be the value of x. In a communication system, this can happen only in a case where you communicate without errors at all. Whatever you send, you receive it as is, right? So in a communication system, if you have a transmitter, and we assume that what's coming from the transmitter is what we call x, okay? And this goes through, typically goes through some channel, and then at the output of the channel is what you read at the receiver side. And let's call that y. If that channel does not do anything to the input, so it produces it exactly the same at the output, this means whatever the transmitter is sending, you are exactly getting it here, which means that the H in this case, so for error-free communication, no errors at all, which is impossible practically, okay? For error-free communication, H of x given y is equal to 0. But this is impossible practically, because this means you are not really going through a realistic channel. There is no such a thing like a communication channel, whether it's wired or wireless, without any errors. Why? Because the minimum that you can have from your knowledge in communication, the minimum problem that you can have with the channel is what? Noise, right? Where does noise come from? Electronics of what?
Of the receiver.
Yes. So keep this in mind, okay? What happens is you send a signal out of your transmitter, whether your transmitter is connected by a cable or by wireless or whatever, that signal goes through the channel. Assume that you have a very nice setup, so no walls, no reflectors, nothing. You are working in the open desert and the transmitter and the receiver are close to each other. So in that case, the only effect is going to be that that signal is going to be received and read by some electronics in the receiver. And electronics at any temperature higher than the absolute zero, minus 372, or sorry, 273, right? So any temperature higher than that will cause the electrons in the receiver components, which are resistors and transistors and so on, will cause them to move randomly, which is gonna somehow disturb a little bit your voltages coming out of the electronics, and this is what we call noise. So noise is always there because there are no electronics without noise, except if we manage somehow to get to minus 273 Celsius, which is again from the laws of thermodynamics and some other stuff is impossible. So because you need infinite energy to cool anything to that temperature, right? So noise is always there, and it is tied with the receiver. So keep that in mind. If you have two receivers, same signal transmitted from the source, and it's read by two different receivers, RX1 and RX2, then you have noise 1 and you have noise 2. They are not the same. But if you have two signals coming from two sources, right, but they are both received by the same receiver, then you have only one N, one noise only. So the noise is always related to the receiver, okay? The random value, the random changes in the signal due to electronics is always tied to the receiver, not the transmitter, okay? That's one important concept as a refresher for your communication. Going back here, any communication channel will at least have noise added at the receiver, which means that I send X, I receive Y, which is equal to X plus some noise, right? So I don't receive exactly the same signal. And the problem with noise is it's random, right? So it's doing some change, some random change to my X. And now, based on how random is this, we are going to have some entropy here, okay? So H of X given Y is gonna be non-zero value for any practical communication system, because you cannot really receive exactly what you transmitted, because of the noise at least. There are many other reasons, but the minimum is the existence of noise, okay? Now, how much? Now, if you have a very bad communication system where, for example, your signal is very, very small, so this X is a very small voltage, while your noise is much higher, then what happens is your noise is gonna scramble out the signal at all, and you end up receiving only noise. In this case, what will happen? Y and X will be independent from each other, because what you are receiving is just noise. Has nothing to do with what was transmitted from the source, right? So in that case, H of X given Y is gonna be the maximum value. What is the maximum value for this? No. Look at the definition. So what happens when you have X and Y independent? What happens to this probability and what happens to this probability?
The probability will increase.
Probability of X multiplied by probability of Y.
Okay, and what happens to this conditional probability? The probability of X given Y if X and Y are independent. This resolves down to what?
The probability of X and the probability of Y will multiply.
No, the conditional, not this one. Okay. Okay. We have this defined as, so H of X given Y is defined as the summation of the probability of X comma Y. So that's the joint probability multiplied by log to the base 2, 1 over the probability of X given Y. From your probability course, when you have two random variables, X and Y, and they are independent, first of all, this resolves into the probability of X times the probability of Y, right?
Yes.
Okay. And this resolves into what?
Probability of X only.
Yes. So the conditional probability of x given y when x and y are independent is the same as the probability of x. Because knowing y did not really change anything. Probability of x stays the same. Right? Knowing y does not add any information, so my uncertainty about x stays the same. It's p of x, right? So this becomes p of x. These two things happens in case of independent. So what this formula becomes? Summation p of x, right? The summation here is over x and y, of course, okay? P of x multiplied by p of y multiplied by log to the base 2, 1 over p of x, right? This part with the summation over x only is what? H of x, right? That's the definition of h of x. P of x multiplied by log 1 over p of x, right? And this part, when I sum over y, will give me 1. I sum probability of y over all possible values of y, that's 1. So the end result is h of x. So for the case of independence, the uncertainty about x given y stays the same. It's the uncertainty about x, because given y did not add anything for me. So the maximum value for the conditional entropy, right, is the entropy of the independent, the unknown part, not the given part, the unknown part. Okay? Clear? So again, by interpretation, this is the ambiguity about x. This is the ambiguity about x knowing y. But if knowing y tells me nothing about x, then my ambiguity stays the same about x, right? So it stays as h of x. That's by interpretation without any mathematical derivation. خلاص? Clear?
Doctor, I have a question.
Yes.
But not here. It's about x and y in communication system. What is y exactly in the communication system?
I will tell you. We will come to this just in the next step. Okay? So there are two possibilities to look at this. Okay? Let's talk about the situation of I have a transmitter. This is just communication. No security issue. Okay? And the signal coming out of the source, we call that X. The signal goes through my channel. And the outcome from that channel, I call it Y. And this is what my receiver is reading. Okay? Now, in this case, ideally, what do I want? Do I want h of x given y to be a large number or a small number for a successful communication, for a good communication? What's the objective of a good communication? That by reading y, I know x correctly. Right? That's the objective of a communication system. When I receive y, I will be able to figure out what x was. Right? If I want this, then I want this to go down or up. H of x given y. Zero, the ideal case. But generally, I want it to be reduced as much as possible. The more it is reduced, so this is what I want in the case of communication system. I want it to be reduced. And the more it is reduced, the less errors I will make. Okay, so the more that I reduce my ambiguity about x when I read what I receive, which is y. Y is the signal that comes to me as a receiver, and that's what I have at hand. Now, looking at that, I need to figure out what x was, right? So the more I was able to do this correctly, the better my communication is, the more reliable my communication is, right? And this happens when this entropy is reduced. Let's take a very simple practical explanation. What do I mean by this a little bit further? The transmitter is sending ones and zeros, and let's say that the 1 is represented by a positive 1 voltage, and a 0, this is from a transmitter point of view, is represented by a negative 1 voltage. Okay. Why did I give E to the voltage? Positive 1 voltage, okay? And a 0, so this is a logical 1, and a logical 0 from the transmitter is represented by a negative 1 volt, okay? This goes through the channel, which means this goes through a cable or a wireless, and then it is read at the receiver. But when I read it at the receiver, what I get actually is positive 1 in the case of 1 being transmitted, or negative 1, and then added to it some value that comes from the noise of the electronics at the receiver. And that noise, by the way, has some distribution. We call it a Gaussian distribution or a normal distribution, right? And it can take any value from minus infinity to infinity. Realistically, it can take. Of course, in an electronic system, it can, if this electronic system is operating on a 5 voltage source, then it can take any value from +5 to -5. It cannot go beyond what the source is doing, right? Because there is no source to bring higher voltages, okay? So sometimes I will receive this plus maybe a 0.1 volt, or maybe receive this minus 1.2 volt, for example, right? Depends on what's the noise value. So sometimes I'm going to receive, if a 1 was transmitted, I'm going to receive this. Another time, I'm going to receive +1 minus 1.2. I'm just taking the case of 1, okay? Now, what do I do as a receiver? I receive this signal, and I have to take a decision. Was the data at the transmitter 1 or 0, right? So a simple decision rule is going to be, I'm going to put a threshold at 0. If the voltage that I receive, which is this whole thing, is above 0, I will assume that the transmitter was sending a 1. And if the voltage is lower than 0, I will assume that the transmitter was sending a 0. So in this case, I will detect correctly a 1. But if the noise was doing this effect, I will mistakenly figure out that the transmitter was sending a 0, right? And this is the case where we say a bit error has occurred because of the noise, okay? Now, the higher the value of this voltage compared to what we call the noise variance, that's a parameter of the noise itself, okay, as a distribution, the less the possibility that I will get this situation, which means the less mistakes I will make, which means the lower this is going to be. خلاص? This is just mapping what we are talking about theoretically into what happens in an actual system. خلاص? So what do you want to do in an actual system to make sure that you have less errors? You increase the amplitude of your voltage, which means increase the transmitted power. The more power you put into the transmission, the less. But of course, power does not come for free. You have to pay for it, right? So you cannot really keep improving the system and pay more and more and more for it. So you have to stop at some point, which is your acceptable rate of errors. خلاص كده clear how we map these theoretical things into actual communication system. تمام? Anyways, this is the case of communicating. Now, let's look at another very interesting scenario. I have a source. This source is doing encryption. So inside the source, there is an encryption process. So I have data, and then the data goes through encryption, and the output from the source, okay, we call that Z, while the data coming from the source, we call that X, okay? The output is the encrypted data. We call that Z, okay? And then, or let's not call it Z. Let's give it a slightly different name because I want to use Z for something else. Okay. So let's give that like XE, the encrypted. Okay, so it's another, it's not X, it's something else, which is the encrypted one. Okay, and then this data goes through the channel, okay, we'll call it channel 1, to the intended receiver, and at the intended receiver, I receive something which is Y, right? This goes to, if this transmitter is Alice, then this goes to Bob, receiver, right? And these are two legitimate guys. Now, Bob has the key, so Bob can actually recover the original unencrypted from Y with some errors because still there is some noise added here, right? So it's not exactly XE that he receives. The Y here is slightly different from XE, okay? But using the decryption, he can approximate that Y to some X, and sometimes the approximation is gonna get the correct X, sometimes no, only because of the noise. But Bob has the key, so can recover X or an approximation of X from Y, okay? Because it can decrypt, so it can do this conversion back, okay? That's for Bob. Now I have, of course, because the channel is dependent on the receiver, I have another channel with another noise that connects this to an eavesdropper. So I have here Eve, okay? And that's receiver number 2. Now Eve does not have a key, right? So what Eve is receiving is Z. We call it Z, which is XE with some noise. So Z is equal to XE plus some noise. And Y here, we can say, because I have the decryption capability, then I can say that Y is equal to some X plus some noise. Okay, so there is a difference. One of them can recover the original, but with some noise added to it, right? The other one cannot recover the original. The only thing that she can see, the Eve, is actually the encrypted data. I cannot really get the original data, okay? Now, what do I want in terms of H of X given Z and H of X given Y? What do I want? For a communication, this is H of X given Y, right? It's the actual communication. So I still want this to be as successful as possible. So I want this to be small as possible, right? Now for protection of information, what do I want to do? I want to make sure that this goes to the maximum possible value, right? And what's the maximum possible value here? La. H of X. Cannot go beyond that, right? So I want to make whatever this guy is receiving completely independent from X, right?
Oh, okay. Yes.
Right? Okay. Okay. So how do I do that? By selecting a key that's used here for encryption, which is very difficult to guess or has certain properties, right? And that key, when it's combined with the information, it's impossible at the receiver to relate the encrypted data to the actual data. I cannot figure out that relation, okay? In that case, I will make Z independent from X, and I will make sure that the eavesdropper cannot really figure out anything about my source. Of course, the source has a limited, if the source has 5 possibilities, and I keep sending the data for an infinite number of time, eventually I can figure out what's the probability of each one of those, right? But that's a different story, because anyways, because the source has limited possible outcomes, then there is the H of the source, which I cannot go beyond, right? I cannot make the ambiguity higher than the H of the source. Because without anything, if I don't know anything about that source, I still need to resolve that ambiguity, right? Okay, without receiving anything. Here, I receive something. If I make it independent, it looks like I'm not receiving anything, right? And in that case, I will maximize this entropy. I will make sure that I protect my information from the eavesdropping by making sure that what the eavesdropper is reading is totally independent from X. And this can only happen if this X encrypted is totally independent from X. Because that's what the eavesdropper is seeing. It's seeing XE with some noise. And we know that the noise gives you some errors but does not make everything independent, right? So the only way is to make this itself independent, which is this one. Okay? While for the intended receiver, I want to make sure that what they receive is as close as possible to the source, and I make sure that this is the case by giving them the key. So they can recover back the original information, of course with some noise again. Okay? So for communication, as low as possible. For protection and encryption, for the eavesdropper, I want to make sure that H of X given what leaks to the eavesdropper is the highest possible, which means that I want to make sure that what the eavesdropper sees is totally independent from the actual information. Okay, by doing encryption. That's the function of the encryption. Okay? So you see now that this H of X given Y is a very important quantity. For communication, we want to reduce it. For eavesdropper, we want to make sure using encryption that it is a very high, value.
Can we make X and XE totally independent?
Yes, by using, that's what we will discuss when we go to Shannon's perfect secrecy. It's gonna be very simple. By combining X with a key, which is completely randomly generated and totally independent from X. So if you take X and you combine it using a certain combination operation with some random value that's totally independent from X, then in this case, the outcome is gonna be completely random independent of X. Okay? And that operation is multiplication, but multiplication in the binary domain is the XORing operation. So you generate a key that has to be as long as the actual data, at least, or longer. And then you XOR the data with that key. And the result, if that key was generated from a pure randomness, totally independent, the result of that XORing is going to be something totally independent from the data X. Okay? And the only way to make it back dependent on the data X to XOR exactly with the same key.
So each time the message will be random?
To each time we'll generate a new key. That's why perfect secrecy is impossible in terms of efficiency. Okay? We call that technique the one-time pad, and that's kind of the suggested perfect secrecy by Shannon, but it's kind of a theoretical limit. Practically, you cannot do that.
Yeah, because like how the receiver will know the shared key?
I have to share it with the receiver every time. So imagine every time I do this, I have to share it first and making sure nobody else gets it, right? And then send the data encrypted with it. That's why it's very inefficient. Okay? Yeah. Any questions? Okay. So another mathematical tool, variation of the entropy, but it does not really have that much meaning, okay, in terms of a communication system, is something called the joint entropy. And the joint entropy is defined as, I mean, here you can see how to mathematically calculate it, okay, but eventually this becomes the joint between X and Y is equal to the entropy of Y plus the entropy of X given Y, or it's H, the same, will give you the same result. H of X plus H of Y given X. So this or this will give you exactly the same thing, which is this one. H of X comma Y, okay? And this is always less than or equal to the sum of the two entropies of X and Y, right? The equality will happen when X and Y are independent. And if X and Y are independent, then this becomes what? H of X. So you can see that in the case they are independent, this becomes simply this side of the equation or of the inequality, right? Okay, so that's, sorry?
What is it?
The joint entropy, as I said, it's a nice mathematical tool that you can use for certain derivations, but it doesn't have that much meaning in terms of looking at what it represents in the communication system. The more important quantity that has a meaning in a communication system, and it's not easy to interpret it from the equation, okay, is something called the mutual information. The mutual information between two random variables, X and Y, which is always written in this form, so you have a semicolon between them, you don't have a comma here, so it's not a joint, it's a mutual information between those X and Y, right, is equal to, forget about this, but look at this. It's equal to the entropy of X, the first one, minus the entropy of X given Y. Okay? Can you interpret what does this mean, this quantity? Remember, H of X is the unambiguity, or sorry, the ambiguity about X in general, without having any prior knowledge. So you don't know anything, then your ambiguity about X is H of X, okay? And H of X given Y is the remaining ambiguity about X when you already know Y, right? Now when you subtract this from this, what do you get?
Like how Y affects X
Close. Affects it in which way?
in terms of like knowing what is it.
Yeah, so in terms of getting more knowledge about X,
Yes.
right? So the mutual information is how much I know about X if I know Y. So that's the opposite of what this guy was saying, right? This guy says how much I still don't know about X when I know Y, right? Mutual information says how much I know about X when I know Y. Okay? So now, given this interpretation, if I have a communication system, TX, RX, and I'm sending X from the source through the channel, I receive Y. Do I want X semicolon Y to be large or small for a good communication system? Large, because it tells me how much I know about X when I know Y. And in a communication system, I know Y. And what do I want to achieve? I want to exactly know what's X, right? So I want this quantity to be as large as possible, okay? That's called the mutual information. Why we care about the mutual information?